Okay, in last class we have discussed an IIR filter design technique using approximation of derivative. Today we will discuss another method for designing of IIR called Impulse Invariant Method. In the Impulse Invariant Method, our objective is to design an IIR filter. Objective is to design an IIR filter having a unit sample response action, that is sampled version of impulse response of the analog filter. So in previous case we have used derivative approximation. In this case we will use the impulse invariant method. Point is, we will apply impulse analog and digital system, and we will design filter such that system response is invariant. That means it does not changes when we apply to an analog system or we apply to a digital system. So we can write Hn is equivalent to Hnt, where n is equal to 0, 1, 2, so on. And T is the sampling input, and Fs is equal to 1 by 2, which we already knew. So the point is, if we have an analog filter, provide an input for xt, then the output will be yt. And for similarly for a digital filter, if the input is xnt, output will be ynt. That is equivalent input leads to equivalent outputs, and that type of system we called invariant system. So we already knew one type of invariant system, that is called LTI system, linear time invariant system. In that particular case, the output should not change with respect to time, but in this case we are changing the system and telling the same input, and we want output doesn't change with the change in the system. So that type of system we call invariant system. and simplest invariant system to be designed is impulse invariant. So that is our objective. We'll have an impulse response for both analog filter and digital filter, and we expect that output should be invariant of system. Now we will start our discussion with analog part, and let's say for the analog filter, HAS is the transfer function, with no repeated roots. Then we can write HAS as summation k equals to 1 to n AK over S plus PK. Now from this we can find poles of HAS are located at S is equal to minus of P, and AK is the residue at S is equal to minus. Then if we take inverse of Laplace transform, we will get H AT equals to summation k equals to 1 to n AK exponential minus pk t. This part we have already discussed with the support lecture for the stability of the Laplace transform. So next step is sampling at t is equal to nt. Then HA and t will be equal to summation k equals to n 1 to n k equals to 1 to n AK exponential minus pk nt u nt. Now we can write HA and t as HN and u and t as un. Then we will write HAN will be equal to summation k equals to 1 to n AK exponential minus pk t to the power n u. Now if we take Z transform of HAN, we get HZ equals to summation n equals to minus infinity to infinity HAN z to the power minus n. Now, if you substitute the value, we can clearly find out this un will make this bilateral sequence into a unilateral sequence, and it will start from n equals to 0 infinity. Then we'll have summation k equals to 1 to n ak exponential minus pk t to the power n multiplied with just to the power minus. What we can do is we can interchange these sequences and we can make this k is equal to 1 to n, then ak, then summation n equals to 0 to infinity exponential minus pk t z to the power minus 1 to the power n. Now this is a geometric progression, so we can write this term as summation k equals to 1 to n ak over the sum of infinite geometric series will be 1 minus exponential minus pk t z minus, and this is our term of h. Now if we want to find out the poles of hz lies 1 minus exponential minus pk t z to the power minus 1 equals to 0. So it will be exponential minus pk t z inverse equal to 1. So z will be equal to exponential minus pk. So poles are located at z equals to exponential minus pk. Now if we compare HAS and HZ, we get 1 by S plus PK compared to 1 over 1 minus exponential minus PK to Z inverse. And if we substitute S is equal to sigma plus j omega. Now we want to first analyze at the imaginary axis, that is on j omega, because this axis will define if frequency response will exist or not. That means sigma will go to 0 and z is equal to exponential j omega. Then HA omega will be equal to 1 over j omega plus pk, and h omega will be equal to 1 over 1 minus exponential minus pkt exponential minus j omega. Now first case we are taking is case 1 for the DC gain at 0 frequency. So we want to match analog response with digital response, and case first we are taking for DC gain. Now for DC gain, h omega at omega is equal to 0 will be equal to 1 by 2. Next is h omega at omega equals to 0 will be equal to 1 over 1 minus exponential minus pk. Now these two terms should be matched, then only these analog and digital response should be matched, then only design will be impulse invariant. So to achieve that, we can do one thing, see that we can reduce the sampling interval. That is T reduced, then sampling frequency will be increased. If we do this, then exponential minus pkt will be very small quantity, and it can be approximately written as 1 minus pk. Now for very small p, very small t, h omega at omega is equal to 0 will be equal to 1 upon 1 minus pk t, and if we solve it will be 1 by pk t. Now comparing with h omega at omega is equal to 0, comparing with h omega at omega is equal to 0, h omega at omega is equal to 0 involves a term 1 by t x. To exactly match DC gain, we can modify the digital transformation by h n equals to t into h a n t. Now this will add an value of t into the numerator side, which will later on cancel the same part. Then hn will be ha nt into t will be equal to t summation k equals to 1 to n ak exponential minus pk t n into un. Then the transform is hz equals to summation k equals to 1 to n ak tak over 1 minus exponential minus pkt z inverse. Then for h omega at omega is equal to 0, it will be p over 1 minus exponential minus pk t. For a small value of it will be equal to p over 1 minus 1 minus pk which will give 1 by pk, which is equal to DC gain of analog filter. Now comparing the poles of digital and analog filter, we can see S is equal to minus pk for analog and Z is equal to exponential minus pkt for digital. Then we can write Z is equal to exponential st. It is a very important relation. It gives a direct relation between Z and S in impulse invariant system. Now we know Hz is equals to summation n equals to 0 to infinity Hn Z minus n. We have taken n is equal to 0 to make the system possible, and for Hz Z equals to e to the power st will be equal to summation n equals to 0 to infinity Hn e to the power minus st. Then the mapping of points from S plane to Z plane can be done by Z is equal to e to the power st, where we know Z is equal to r into e to the power j omega and S is equal to sigma plus j omega. Substituting, we will get r into e to the power j omega equals to exponential sigma plus j omega t. That will give r exponential j omega is equal to exponential sigma t exponential j omega t. Now one can see r is equal to exponential sigma t and exponential j omega is equal to exponential j omega. So omega is equal to omega t. Now observations. We will observe some points from this relation. First point is, for all poles located at j omega axis, that is sigma will be equal to 0, then r is equals to 1. That's mean in S plane is sigma and this is j omega. For all the poles located in j omega axis can be mapped as imaginary z and this is real z for r equals to 1, where this r is magnitude of imaginary and real part, that is real z square plus imaginary z square. So that's mean this unit circle all the poles will be mapped. All the poles will be mapped in this unit circle. All the poles at j omega axis will be mapped on the unit circle of z plane. So this is our first observation. Second observation is all the poles located at left hand plane of S plane will be mapped inside the unit circle. We will take the example. Let's say S1 is equal to minus sigma 1 plus j omega. S2 is minus sigma 2 plus j omega. Then the equivalent Z1 will be e to the power S1t, which is exponential minus sigma 1t exponential j omega t. Similarly for Z2 will be equal to exponential S2t will be equal to exponential minus sigma 2t into exponential j omega. We can find out this exponential minus sigma 1t will be always less than 1. So the mod of this Z1 will be always less than 1. Similarly the mod of Z2 will be always less than 1. Third observation is all the poles located at right hand plane of S plane will be mapped outside the unit circle. You can see S1 is equal to sigma 1 plus j omega and S2 is equal to sigma 2 plus j omega. For that Z1 will be equal to exponential S1t, which is equal to exponential sigma 1 t into exponential j omega t, and Z2 will be equal to exponential S2t will be equal to exponential sigma 2t to exponential j omega t. Now we will try to represent observation 1 and observation 2. So we have this j omega axis, then we have this sigma axis. So we have one pole located at this sigma 1, another at j omega. They are working at same j omega, so this is sigma 1, sigma 2. Then we have another pole this is at sigma 2 and this is sigma 1 with a negative sign. So the mapping will be done in z plane, that is imaginary z with real z, and we have a unit circle. So those poles will be located at a frequency of j omega. So let's say it is this one, this is j omega, and then this poles will be located sigma 1 and sigma 2. Now for the poles with sigma 2 and sigma 1 will be located in the same line but outside the unit circle. So sigma 2 will lie here and sigma 1 will lie here. So this is the mapping for the poles who are at the left hand plane, which will go inside the unit circle, and this is the mapping of the poles who are at right hand plane, will go outside the unit circle. So this validates this stability point. In analog, poles should be in left hand plane for this stability. In digital, poles should be inside unit circle for stability. So that's mean if a system is unstable in analog domain, it will remain unstable in digital domain. If a system is stable in analog domain, then system will remain stable in digital domain. So this mapping does the important part. So now we have done with the 3 observations. Next is 4th observation. This will be omega t as it is equal to omega. J omega is for the analog domain. Now we will discuss the 4th observation is that the mapping between S plane to Z plane is not one-on-one mapping, but it is many to one map. We'll see the example. Let's say S1 is equal to minus sigma 1 plus j omega. Then we have S2 which is minus sigma 1 plus j omega plus 2 pi by 2. Then we have S3 with minus sigma 1 plus j omega plus 4 pi by 2. Then if we want to find out the equivalent mapping in Z domain will be Z1 equals to exponential S2 which is equal to exponential minus sigma 1 t into exponential j omega t, right? Then Z2 is exponential st, which is exponential minus sigma 1t into exponential j omega t into exponential j 2 pi by t into t. Now if we solve, this t will be cancelled out, and exponential j 2 pi is nothing but 1. Then we can find out the value of z3. Z3 is also e to the power st. So it was s1t, s2t, this is s3t, this is exponential minus sigma 1 t, then exponential j omega t multiplied with exponential j 4 pi t into t. If this goes, so it will be j 4 pi, which is again nothing but 1. So what does it mean? If we see from the representation, we have a j omega axis, and then we have a sigma axis, and we want to map S domain in Z domain. So it is imaginary Z, it is real Z. Obviously unit circle is an important part of Z domain, so we will plot a unit circle here. Now what we have done, we have made the points sigma 1 common. So in real axis, this is the point where sigma 1 is minus. Now this point is j omega. So we are saying it is j omega. So then after 2 pi by t, it will be here j omega plus 2 pi by t, and then after some point it will be j omega plus 4 pi by 2, and it will so go on. So the first pole is located at this position, second pole is located at this position, third pole is located at this position. We can clearly see all these poles are located at different points as their frequencies are different, right? But in Z domain, if you want to implement, then let's say this is the omega t, and we have a line from unit circle here. Obviously it is going in left hand plane, so these poles will have to be mapped inside this unit circle. So all these poles, we can see from this particular point, all these poles z1, z2, z3 are exponential minus sigma 1t, exponential minus sigma 1t, exponential minus sigma 1t, and j omega t, exponential j omega t, and exponential j omega t. So all are located at the same frequency, that is omega t is equal to omega, as we have already find out. So this is the point, that is exponential minus sigma 1 t. The poles are located at this point. The mapping is not 1 to 1 but many to 1. So it goes to this point. This point is mapped to this point. This pole is also mapped to this point. And also this pole is also mapped to this point. All the poles with same real part that is sigma with frequency varying by 2 pi by t will be mapped at same point in Z domain. So in impulse invariant method, the mapping is many to one instead of one on one.